Yes, it did. Okay, so this is section 4.2. This is what we have left from chapter 1. I'm sorry, from chapter 4, from 4.1 through 4.8 without 4.6. The reason why I didn't go through 4.6 is because it just uses tables of integrals. So you have to just look it up in a table. We can do that too. But I'm not going to test you on that. So 4.2, we're looking at two theorems. One is Rawls' theorem. Rawls' theorem. And here's what Rawls' theorem says. First of all, it has three hypotheses. I think this should be S, E, S. Okay, three hypotheses. Number one, and I'm going to graph a function that fulfills the conditions. Condition number one, f is continuous. Condition number two, f is differentiable, and I should write on the closed interval a comma b, and differentiable on the open interval a comma b. And here's the third condition, and you notice what the third condition is. F of a equals f of b. If all these three conditions are fulfilled, then by Rawls' theorem, there exists a number c in the open interval a comma b such that, what do you think? Awesome. Here it is. That's it. Let's look at an application. Back to 4.2. On page 288. Let's look at 3.
Question, can you repeat what Rawls' theorem?
There exists a number c in the open interval a comma b such that f prime of c is 0. In other words, the function must have a turn. So if it starts at this point and comes back at this point, it must have at least one turn, being continuous and differentiable. Can it have more than one? Yes, it can do this. So it has more than one c, where f prime of c is 0. Right? So a function that is continuous and differentiable to start at one point and end at another point on the same interval, it must have at least one turn. So let me give you another graph. So between these 2 points, the function can do this. So in this case, there is a C1, there is a C2, and there is a C3, for which f prime is 0. So it's guaranteed that there is at least one in the interval a comma b. Is that better? So 3 on page 288. Verify that the function satisfies the 3 hypotheses of Rawls' theorem on the given interval. Then find all numbers c that satisfy the conclusion of Rawls' theorem. So here's the function f of x, the square root of x minus 1/3 x. And the given interval is 0 to 9. we have to verify three hypotheses. Number one, f is continuous on the interval 0, 9 because it's a difference of two continuous functions on 0, 9, as a difference of two continuous functions on 0, 9. Condition number two, f is differentiable on 0, 9 as a difference of two differentiable functions on 0, 9 open, as a difference of two differentiable functions on 0, 9. Now, number three, I have to find f is differentiable on the interval 0, 9 as a difference of two differentiable functions on 0, 9. Is that okay?
No.
We know that the sum or the difference of two differentiable functions is also differentiable. The sum or the difference of two continuous functions is also continuous. So first I have to state the first hypothesis, which says that the function is continuous. Yes, it's a difference of two continuous functions. This is continuous everywhere on 0, 9, and this is continuous everywhere on 0, 9. So then their difference must be continuous on 0, 9. The square root of x is not differentiable at 0, but the theorem requires the open interval 0, 9. So I don't care whether it's not differentiable at the endpoints. It's possible. So the square root of x is not differentiable at 0. It's 1 over 2 the square root of x, which is not defined at 0. So the derivative of this, but it doesn't matter because 0, 9, this interval does not include 0.
It doesn't include 9.
It does not include 9, although it's differentiable at 9. Okay, so the function f is differentiable on the open interval 0, 9 as a difference of two differentiable functions on 0, 9. Better? Okay, so now I have to find f of 0 and I have to find f of 9. If they're not equal, then I will say Rolle's theorem is not applicable. But if they are equal, and the top is the 0, when I plug in 0, I get 0. The square root of 9 is 3.
1/3 3 of 9 is 3.
Yes, so it's 0. Then I will say from 1 and 2 and 3, comma, by Rolle's theorem, I will find there exists at least one x value c in the open interval 0, 9 such that f prime of c is 0. So by 1, 2, and 3, from 1, 2, and 3, and by Rolle's theorem, I will find at least one point where the function turns. In other words, it has f prime 0. Now I have to find f prime of x, which is 1 over 2 the square root of x and minus 1/3. Then I have to create this function in which I replace x by c. So 1 over 2 the square root of c minus 1/3 equals 0. And now I will solve for c. And whatever I get, 1 or 2 or 3 numbers, they must be where? Guaranteed by Rolle's theorem.
Between 1 and 9.
Between 0 and 9.
Or 0.
Yes, very good, awesome. So then I will move 1/3, so 1 over 2 the square root of c equals 1/3. If two fractions are equal and their numerators are equal, what must happen? Or you say, forget it, I will just cross multiply. I don't want to think in those terms. But if two fractions are equal and their numerators are equal, obviously the denominators must be the same. There is no question. or you just cross multiply. So 2 the square root of c equals 3. Yes, I will divide both sides by 2 and then square both sides. So I get 1c, which is 9/4. And this, it better be between 0 and 9. So the only c between 0 and 9 guaranteed by Rolle's theorem is 9/4. So at that point, the function must have a max or a min. And this is valid for any function that fulfills these 3 conditions. Continuous and differentiable, continuous on the closed interval, differentiable on the open interval, and having starting and ending at the same point. We must have at least one term. Now, the other theorem is based on Rolle's theorem, has only the first 2 hypotheses. It does not require the third one. And it's called the mean value theorem. The mean value theorem. Let's look at the graph and decide together what's happening here. Here's the graph. There's no requirement for starting and ending at the same point. This is still on a comma b. This is still f of x. This is point A and point B. Can anyone give us the coordinate, the y coordinate of A? Thank you very much. And the y coordinate of B? Can anyone give us the slope of the line AB? So far, so good? Okay. Here's what I'm going to do next. Not before I write the 2 hypotheses of this theorem. So number 1 is f is continuous on the interval a comma b. Agreed? 2, f is differentiable on the interval a comma b. And here's what I'm going to do next. Ready? Ready? So I'm going to draw a parallel to this line at that point and draw the tangent. Doesn't matter how you want to call this. But it's guaranteed that. Can anyone give us the slope of this line? The slope of this.
F of B minus F of A over B minus A.
Perfect. And in another way, that's awesome. Yes, of course. Parallel lines have to have the same slope. But is there another way in which?
B minus A equals F of B minus F of A.
No. Exactly. So, if a function is continuous on the closed interval a comma b and differentiable on the open interval a comma b, then by MVT, mean value theorem, there exists a c in the open interval a comma b such that what? Awesome. Equals?
F of A minus.
This is it. It's guaranteed by MVT. Sure. So if we have a function that is continuous on a closed interval, a comma b, and differentiable on the open interval, a comma b. We don't care what happens at the endpoints. Then there must be a value, c, in the open interval, a comma b, where f prime of c equals, and this is basically the same thing, right? So f prime of, right? So this is the slope of this line, which is 0. But this is the general case. So this is for a specific case. It's the same idea. So let's see how we apply the mean value theorem. Verify that the function satisfies the hypothesis of the mean value theorem on the given interval. Then find all numbers c that satisfy the conclusion of the mean value theorem.
Do 11.
Let's do 11. Good pick.
Do we have college tomorrow?
Yes.
Okay.
Yes. Yes. We're open tomorrow. So f of x equals natural log x on the closed interval 1, 4. So I have to state condition number 1. Caesar, you had a question?
I think it's the next video.
Did I copy something else?
No,
I always do.
it's 289, but we can figure it out.
Oh, 89. Sorry. Thank you. Sorry. So first we write that f is continuous on the interval 1, 4. This function is continuous everywhere between 0 and infinity. That's its domain. And number 2, f is differentiable on the open interval 1, 4. That's good enough. And then we'll say by MVT, there exists a c in the open interval 1, 4 such that, can anyone dictate now?
F prime of C
Very good. Equals f of,
4
very good,
minus 7 over 4 minus 1.
awesome.
Can you, this is going to,
Yes.
might yell at me.
No, never.
Explain what f is differentiable means again.
Yes. Yes.
Betty.
A function is differentiable if several conditions are fulfilled. Continuous everywhere, no cusp, corner, or vertical tangent.
Okay.
In other words, it has a unique tangent at any point on that interval. Not two tangents, and not a vertical tangent. Better? Good. Other questions? Okay, so I have to find f prime of x first, which is 1 over x. Then the left-hand side will be 1 over c. And I have to figure out the right-hand side. The denominator is definitely 3. Now, how much is f of 4? I have no idea. It's natural log 4. But how much is natural log 1? Correct. Very good. So again, whatever you want to do, in this case, I would do this. In any proportion, I can do this. You can say, forget it, I'll cross multiply. That's fine too. But this is basically c equals 3 over natural log 4. This better be in the interval. What interval?
1 and 4.
Yes, very good. So let's check. I'm going to check with the graphing calculator. Make sure. So divide by natural log 4, and I get 2.16 approximately.
And that works because it's in between 1 and 4.
It must be between 1 and 4. It's guaranteed by the mean value theorem. Now I'm open to any type of problem you would like to go back to. If you want to go back to this, we can start this. If you say, I want to see a problem like that, or something from this section or that section, Or we start with this, and then at the end we'll say, oh, we need more problems of such and such.
Do that.
Do you have anything else in mind for now?
I didn't really have a question about
Yes.
the specific
Yes,
problem
yes,
or anything, but
yes,
on the Newton's method,
yes.
you said that there's how exactly you said that there's a for your initial n.
For initial value for x0.
There's a good way, or there's a way to find what that initial value should be.
You have to plug in numbers and find a 1 unit interval. And then it doesn't matter which one you start with. So if you find that there is a solution between 1 and 2, you can start at 1, you can start at 2. But you have to make sure that f prime of that number is not 0.
Okay.
Because f prime of x0 is in the denominator, and you will not be able to go past the first iteration. You will not be able to find x1. And we'll look at an example as well. Yes, please, Stephen?
Yeah, could you just explain how you got the natural log 4 over 3 again from 1c?
So you mean this one?
Yeah.
How we got this? Okay, so if I have a proportion like this one, okay, so like a over b equals c over d, b over a must equal d over c.
I guess I meant like how you got that 1
This?
over c. Yeah.
So I have to differentiate natural log, which is 1 over x. I have to change this into 1 over c because f prime of x is 1 over x. I have to determine f prime of c, so I have to plug in c here, so it's 1 over c. That's the left-hand side. Then I copy the equal symbol. Now f of 4 is natural log 4
Okay.
minus f of 1 is 0. 4 minus 1 is 3. And then I flip.
Perfect. Thank you.
Better? Other questions here? Everyone okay? Okay, so let's start with this. So we're given a function f of x equals x e to negative x squared over 8, and the interval is negative 1, 4. Find everything. You don't have to graph. No need to graph the function. Just present the ordered pair, the table with ordered pairs, and determine the max min. Do you want me to start, or you want to work on this problem for a couple of minutes?
This isn't in the book?
This is from this.
Work on it for a couple of minutes.
Okay, that's fine. We make a decision whether we want the test on Monday or Wednesday, or you want to think till Wednesday. It's fine by me.
I mean, if we turn it, I like the turning in the extra, or getting a little extra time to work on it. I don't care if it's posted before the test. Like that, I'm fine with that. Like if we take the test Monday still.
Okay. So I heard one
So we have
opinion.
some more time.
So think about it, and we'll talk about it. Make a decision on Wednesday before class. A few minutes before we start on Wednesday. Just think about it and let me know what you decide, and we'll do that. So that's why I'm not sure whether you want to turn in the checklist on Monday, then the test could be Monday or Wednesday. If you say I don't care about the solutions for the checklist, then you can turn it in on Monday and have the test on Monday. If you do care to look at the checklist solutions, then we have to have the test on Wednesday next week.
We'll start the next section.
But I have to start. Yes. Yes, I have to finish for chapter 4 with 4.9, and I have to start chapter 5. Because I'm trying to have at least a full week of review before the final. 4 hours. Okay, so we are working on this.
Professor,
Yes.
I just want to make sure that
Yes.
sometimes I get mixed up.
So yes, that's perfect. But it's over 8, right? It's negative x squared over 8, so when I bring down 2, I have negative 2x over 8. 8 does not go away.
Okay.
Is that clear why?
But then, but the 8 can't.
So when I differentiate this piece, is the same with differentiating this piece. So this is negative 1 over 8 times 2x, which becomes negative x over 4. So the denominator does not go away.
But that's the end of it, right?
Yes. But then I recommend you factor out whatever, change it into a product, so you can solve the equation. So please remember, this is a product. We have to use the product rule. Let me know if you have questions, please.
Stephen,
Yes.
are you not using logarithm differentiation there?
You can't.
Don't you have,
This is a function. You want to differentiate. This is not a function raised to a function. E raised to a function is not a function raised to a function. It's the function e to the x. Yes.
I just want to make sure.
Hold on just one second. Is that clear, John?
yeah.
So e to the x is not a function raised to a function. What happens if it's
right there with you.
Yeah, I'd already gone through logarithms.
We do not apply, this is one function. We want to find its derivative. There is no need to apply natural log. It's not a function raised to a function, right? So one more time, a function raised to a function would be something like this. This is a totally different story. So the base is a function 1 plus 2x. And the exponent is a function which is 1 over x. But here, this is a constant. It's a constant raised to a function. It's e to u. It's not a function with x in it raised to another function with x in it. Is that better? Good. So is that clear? Do you understand the difference between these two? So we do have that function e to u of x, which is not something like this, e to u. Is that okay? So when we differentiate e to u, we get e to u of x times u prime. So what was the confusion here?
Frankly, I'm not quite understanding the difference between the e.
But e is a number. It's 2.7. This is not a number. This is a
but
function.
Didn't you just say that e raised to what u of x? Wait.
See, this is the base here is a number. The base here is a function. Is that okay?
Yeah.
For this, we have a formula or a differentiation rule. For this, we don't. Okay. So let's work on f prime of x together. The first function prime is 1 times e to negative x squared over 8. And then plus x times e to negative x squared over 8 multiplied by negative 2x over 8, which is the inner function prime. Obviously, I will have to pull out,
The e to the negative x squared over 8.
and then I have 1
1.
minus, so I'll simplify, and I get negative x squared over 4. Then inside I will have, so e to negative x squared over 8, and then multiplied by 4 minus x squared over 4. And you already know me, I'm going to factor out negative 1, and then factor into x plus 2x minus 2 over 4 e to x squared over 8. So
Where'd you get the 4 from?
when I add two fractions, I have to find the least common denominator. I have to multiply this by 4. So I have 4 minus x squared over 4. I factor out negative 1, and I get x squared minus 4, which factors into x plus 2x minus 2. So this is the final form for f prime. Any questions on the final form for f prime? Is this okay? Which part is not?
No, just sorry.
So is this not clear, or?
Yeah, I was going the logarithmic route too.
This is a constant. We can't do that. So we have a formula for this, right? We have a differentiation rule for this, which is e to a function prime, e to the function times the function prime. But for this one, we don't. We don't have a formula for this. If this is our function, let's call it g of x, then I can't. I have to apply log to both sides and then differentiate implicitly. Is that okay? So now the first function prime is 1 times the second function plus the first function times the second function prime, e to u times u prime. But u prime is negative 2x over 8. And I will simplify to get 1 over 4, but with minus in front. Are we okay now? So then I factor out x to negative, e to negative x squared over 8. So then I have 1 minus x squared over 4. Find the least common denominator and factor out negative 1. And then I have, this becomes x squared minus 4, which now is x plus 2, x minus 2 over 4 e to x squared over 8. Is that okay? Obviously, no critical number comes from undefined. None. This is always defined. This is always positive. More than that.
Only 0 and 2 because negative is outside the interval.
Yes. So there are two options, x equals 2 and x equals negative 2, but I will not be able to put negative 2 in the interval because it's outside. Not in, it's correct, but it's not in negative 1, 4.
And the e never equals 0. Correct?
No, the graph of e to the x is a increasing function on all its domain will never touch 0. And even if it were a 0, this function will be undefined at the same value of x, so it's not going to be a critical number. So now I have to create a table. F prime f of x from negative 1 to 4. This is how we study a function on a closed interval. And we only have positive 2. Now we'll have to study the sign of the derivative. to the left of 2, I'm going to plug in 0. This is 1. This is 0, 0. Negative 4 with minus in front. What is the sign before 2?
Negative.
Let's do it again. So 0 plus 2 is 2. 0 minus 2 is negative 2. Negative 2 times negative 1 over a positive number. Very good. So now I'm going to plug in 3. This is still positive. 3 plus 2 is positive. 3 minus 2 is positive, but there is a minus in front. Correct. Now I have to determine the function value here, here, and here. So I will plug in the function in the graphing calculator in y equals. So in y equals clear if you have anything, and you plug in x times e in parentheses negative x squared divided by 8 and close the parenthesis. And second in table. And I want negative 1, 2, and 4. Negative 1, 2, and 4. And I got negative 0.9 approximately. At 2, I got 1.21. And I got 0.54. Now the moment of truth. This is when I find my mistakes and see what's happening here. Okay, so from negative 0.9 to 1.2, what does the function do? Right, is that supported by the sign of the first derivative? From 1.21 to 0.54? Good. So now I know that it's coming from this point. It's going up to 1.21, and then it stops at 0.54. You don't have, I'm not graphing the function, I'm just plotting the heights. So then what does this point represent? Very good, indeed. It's not local because it's at the end point. Right. So what type of point is this? 2, 1.21. And local. What point is 4, 0.54? Nothing. So every time I'm asked, in summary, every time I'm asked to study a sign on a closed interval, I find its derivative, I simplify it to the core, I set it equal to 0, and I also find when the derivative is undefined, if that's the case, and then study the sign of the derivative, and then make decisions on which one is a local, which one is an absolute max min. And the endpoint of the interval cannot have absolute, cannot have local. Any questions on this? Okay, let's move on. Verify that the function satisfies the hypothesis with the mean value theorem on the interval negative 2, 2. Find all numbers that satisfy the conclusion of the mean theorem, value theorem. So here's the function. Continuous and differentiable everywhere, correct? So we have f of x, which is x cubed minus 3x plus 2, and the interval is this. But we do have to write it. We have to write that the function is continuous on negative 2, 2 closed as a polynomial function. We have to write that is differentiable on the open interval negative 2, 2. And then find C, or C values, guaranteed by the mean value theorem. So let's do that. Let me know if you need help.
We should put up the notes for the MVT.
Yes. Do we need more time?
A little bit.
Okay.
It's like a minute.
Okay. We agree that the function is continuous. It's a polynomial function. Number two, differentiable everywhere, but also on -2, 2. So there exists C in the open interval -2, 2, such that f prime of C equals f of 2, very good, minus f of over 2 minus -2. Very good. So I have to find the derivative. So f prime of x is 3x squared minus 3. This will be this side as 3c squared minus 3 equals. How much did we get for f of 2?
1.
Okay. How much did we get for f of -2?
It's 4 over 4.
I got.
I meant it's 1 that is in.
It's 4 minus 0 over 4.
That's what I got.
Very good. So then 3c squared minus 3 equals 1 equals 4. So then c squared equals 4/3, which means that c equals, very good. Do they both belong to that interval? Then both are the guaranteed numbers of MVT. If only one, then it's only one. So c equals 2 divided by the square root of 3 with plus or minus. Okay, so they both belong to the interval -2, 2. So in this case, the function has 2 points. It does something like this. Yes, Kelly?
Where's that?
Which one?
Oh, wait, never mind. Sorry.
No problem. Is this clear? Any?
F2 and F-2 are back into the original equation, right? Not the derivative.
No, this is f.
Yeah.
Yes, because remember we discussed f before we even drew the tangent. Yes. Yeah. Moving on. Okay, can we look at this limit now then? Do you have other questions about the previous one? Okay, so we are looking at limit as x approaches 0 from the right, sine x natural log x. So let's work on this. 1 minute. Let me know if you need help.
This was a problem with the checklist, right?
Possible.
I think it
It's
was.
okay. Well,
No, I remember doing it.
that's okay. Okay. Ready? Okay, so first, it's like always, we have to identify the indeterminate case. Maybe it's just 5, and I don't have to do anything, right? So sine, when x approaches 0 from the right, sine approaches
0.
perfect. And natural log, remember the graph, always have this natural log graph in mind. As x approaches 0 from the right, good. Doesn't matter, the sign is not important. We're talking about 0 times infinity. So this is an indeterminate case. So then we have limit as x approaches 0 from the right. I have to do something about this. Hopefully change it into a ratio. And I will not touch natural log. That will be a terrible mistake to try to bring natural log down. Instead, I will replace sine x by 1 over sine x. Because it's the same thing. When I divide by a fraction, I have to flip the fraction, right? Okay. So therefore, when I differentiate now, because this becomes infinity over infinity, because it's 1 over 0 from the right. Now L'Hopital's rule is applicable. So then we have limit as x approaches 0 from the right. The top is 1 over x. And the denominator, you can change the denominator into cosecant x. 1 over sine is cosecant x. So when we differentiate cosecant x, we get negative cosecant cotangent. Any questions so far? Any questions so far? Okay, so let's see what we have next. So this is limit as x approaches 0 from the right from x cosecant x cotangent x. So the top is 1, or if you want, negative 1. Doesn't matter. Now let's see what happens in the denominator. This approaches 0. Cotangent is cosine, say it again,
How did that X?
1 over x times, and I flip the denominator. So I get 1 over x cosecant x cotangent x. I could look at this to see what it is. So cosecant x is 1 over sine x. And this cotangent is cosine x over sine x. So if this is better, you can do this too. And then plug in to see what we come up with. You prefer this than working with cosecant and cotangent? So this product is 1 over cosecant, 1 over sine, I'm sorry, multiplied by cosine over sine, which is cosine over sine squared. So let's flip it then. Limit as x approaches 0 from the right, from negative sine squared x over x times cosine x. So all this is this fraction. So when I divide by it, I have to flip it because it's cosine over sine squared, so it's sine squared over cosine with x in front. This there is no problem, it approaches 1. I don't even really have to use L'Hopital's rule here. I will split this into sine over x like this, limit, this approaches 0 from the right, negative sine x over x times sine x over cosine x. Where does this go? Careful. Exactly. This goes to 1. As x approaches 0, from either side, it doesn't matter, or from both sides, but this is just from the bottom. So this approaches 1, right?
Yeah.
So this approaches 1, this approaches 0, and this approaches 1. So therefore, the final answer is, that's it. Is that clear? Which part is not?
On the first term, in the first term, that's negative sine x over x, at the bottom of the page. You say it's 1, sine x is 1, I get that, but isn't that?
Sine x over x is 1, not sine x. When x approaches 0, sine x approaches 0. But this is a limit that we talked about 2 months ago. So as x approaches 0, the limit of sine x over x approaches 1. A long time ago when we couldn't even use L'Hopital's rule, we graphed it. It was the first exposure to it was to graph it. So then when x approaches 0, sine approaches 0, but cosine approaches 1. So this is no longer an indeterminate case. 0 at the top and 1 at the bottom. So therefore the limit is 0. Do we agree? Other questions down the road? Any questions on the steps that we followed here?
I have
Yes.
Probably a
Yeah.
dumb question.
No dumb question.
Can you reverse log rules? Because like if this was x to the sine x, you would then use log rules.
Yes. Yes, I would. But if you want to bring natural log down,
Well, no, I want to say sine x ln x equals x to the sine x.
you could.
Oh, really?
But yes. But then you're going to have negative infinity to 0. It's a different, a more difficult situation because it's a power. It's one of the indeterminate power cases.
It wouldn't get rid of it.
No, because you can. So you can write it as natural log to sine x, right? But this approaches infinity, this approaches 0, then you are back to an even more sophisticated, more difficult indeterminate case than the product. So the power indeterminate has to be changed into a product and then changed into a ratio. So if I do that, I will go backwards. Very good question, actually. Is this clear? Any questions here? I thought, Nico, you had a question. Is there anyone? Okay, so let's work on the next one. So this one is limit Sx approaches infinity from e to the x plus x raised to 1 over x.